Okay, now I think I'm ready. We'll start our fourth workshop of the semester. This one about matrix elimination. So still solving systems of equations. Same thing we did last week in class and in the previous workshop. But this time we are going to do this using matrices. And it's basically the same thing as doing it with elimination. The way that we write it looks a little different, but the process and the concepts behind it are the exact same. Just a little quick comments here. I see someone in the list of participants whose name just shows up as Zoom user. If you want credit for this in your adapt checklist or whatever, you need to change your name to something that we can recognize, because otherwise we have no idea who you are. All right. So the list of questions that I have for this one are here, you can see. So first, just some simple practice with converting systems of equations to matrices, and then matrices to systems of equations, and then practicing some row operations on matrices. And then we'll do the practice with actually doing matrix elimination properly, the whole thing. Okay, so let's get started here. I think I recognize everyone. Just in case any of you are not students in the Mathematics for Business class, the textbook where all these questions are coming from is right there at the bottom of the screen. All right, first thing we are going to do is converting systems of equations to matrices. All right, our first ones are here. Okay, we're just gonna jump right into these. So everyone, whoever's here, you're gonna have to talk and help give answers. The first one, here, we have a system of equations with two equations here. We want to turn that into a matrix. Are we ready to turn this into a matrix right away? Do we need to maybe rewrite these equations in some manner?
We can rewrite.
Okay.
-9 will be in the other side, but it's easy to do it without this.
Okay, your voice is very quiet. Maybe your microphone sensitivity is low, or just speak a bit closer to your microphone if you can. Sorry, and could you say that one more time for us?
Can you hear me?
All right, that's much better.
Okay, I said that we can move -9 to another side to be their like usual form of equation, but it's easy to do the matrix form without this action.
Okay, you're right. It is still not very hard to turn this into a matrix without that, but just kind of for extreme clarity for everyone, we can do this. So if we write it like this, and then our other equation, the two match, the x's and y's are both on the left, the constants are both on the right. All right, so if we take this and then we turn this into a matrix, then how large will this matrix be? How many rows, how many columns?
Three columns, 2 rows.
All right, two rows, 3 columns. So about this big. And what will our first row be? So there's not too many people here today. You're gonna have to, everyone try to speak up and try to offer answers. First row of this matrix. All right. I'll go ahead and talk through this one. I do hope that people can talk and offer answers to the questions. That lets me know your pace and if you're following along or not. And it's also just a little more exciting than just me talking the whole time. All right, so our first row is just the first equation. We take the constants. So 11, 9, and then the coefficients. And then our constant here is -5. And the second row will do the same thing. 7, 5, -1, like this. If we were to add some labels to this, we could do that. So here's our row 1, here's our row 2. Column 1 here is representing the x's, so 11x and 7x. Column 2 here is representing the y's, so we have our 9 and 5 here. And then our third column is representing the constants, so we label this as RHS for right-hand side of the equation. Right-hand side. If we want to remind ourselves in the matrix where the, let's not do that in red. If we want to remind ourselves in the, that's purple there. If we want to remind ourselves where the equal sign is in the equations that are represented in the matrix, then we can do this and put this vertical line between the coefficients for the variables on the one side and then the constants from the right-hand side on the other side of that line. It's not necessary, and I am not going to be writing that when I do these examples because it just takes extra time. But if we go back to look at the original system we're working with, then it's pretty easy to see where the equal sign should be going. All right, let's do the next one. So here, it's a little bigger. Let's ask this in a slightly different manner here. Can someone tell me what is the second row of this matrix?
Two.
Tell me the whole thing.
2, -1, -1, 4.
-1 and 4. All right. So just reading off the values here. -1 because we have a -1 coefficient on these numbers here. All right, I'll just write in the other ones. I think this is probably not too tricky. 5, -3, 2, and -5. So this is the matrix that represents the system here. Again, not very hard to switch back and forth, just writing the numbers in a box like this. All right, I'll move on to the next two, which is just practicing going the other direction, then some simple operations, and then we'll get to the main thing, which will be the actual elimination process. Okay, so matrices to systems of equations. Let's do the one on the left here first. So here's our matrix, our augmented matrix, because we have this line here, very handy line, reminding us where the equal sign goes. What is the, yeah, let's try this directly. what is the system of equations that is represented by this matrix? What's our first equation?
Two x minus 4y equal -2.
Okay, so 2x minus 4y equals -2. And then our second line?
3x minus 3y equal -1.
Okay. And what color here? For our variables, why did you choose to use x and y here?
Just because we always use them. I can choose everything I want, but it's usual.
Okay, good. So we can choose whatever variables we want. There's no reason it has to be x and y. Excuse me. It's just usually we work with x and y, so it's just sort of convention, maybe easier for people to think about, but our variables could be anything at all. They don't need to be these ones. All right, the system on the right here. So 3 rows. So we're going to have 3 equations here represented in our system. What is the first equation going to be?
So x minus 2y equal -1.
Okay, 2x minus 2y equals -1. We have a 0 here, so we just understand that that represents the z value, so 0 times z. So like we could write that if we really want. Plus 0 z equals -1. We normally don't do that because it's very unnecessary. I'll do that for these ones just to make it very, very clear how the matrix is connected to the system of equations. So for the next one, it's 0x plus 2y minus z equals 2. And 3x plus 2, sorry, that's not 2, 0y minus z equals -2. So there's the matrix on the top, and there's the system of equations down below. And again, normally we would write this without the zeros in there, but I just wanted to do that so you can kind of see how everything lines up. Normally, we would just go straight to this version of this 3x minus equals -2. So there's the matrix and the system that matches. All right, we'll head over to the next part. So just the row operations. Yeah, I do have a slide kind of re-explaining it, but let's try this without first. All right, so our first thing that we're being asked to do here, we're given this matrix and we are asked to swap rows 1 and 2 in this matrix. So I'll write this out. Question A. And we'll write out our matrix, 3 rows, 4 columns, about that big. We'll write out the operation on the side here so we know what we did. So rows 1 and row 2, take R1, and I'll write it like this, little double arrow thing, and row 2 to indicate that we are flipping them. Okay. So what is our new row 1? Remember, we can put these labels here, row 1, row 2, row 3. After doing this operation, what is our new row 1?
We just change their places?
Yeah.
So it will be 4, 1, minus 3, 2.
4, 1, negative 3, and 2. Good. And the new row 2?
2, negative 3, negative 2, negative 4.
Negative 4. And row 3 here is not changing. We're not doing anything to row 3, so that will just be the same thing. All right. So why would we swap rows like this? Like, what is the point of this? The particular swap that we did doesn't seem very useful, but in general, why would we want to swap rows? No reason? Okay, we'll see this in some of the examples we're going to look at later. But if we have a position that we want, let's say, instead of a 4, in this spot, if this was a 1, often we want to have 1s on our main diagonal. But let's say we have a 1 down here in row 2, then we just swap row 1 and row 2 to put our thing that we want sort of in the right spot. We want the 1s to be in the right spots, and we want 0s to be below that main diagonal when we do elimination. So we swap to just put things in the right spots. We can also do these other row operations, multiplying and adding rows together. But swapping, if it doesn't, it won't come up really often, but when you have an opportunity to do it, then it's very nice because it saves you having to do actual like arithmetic work. You could just switch the rows and you get the result you want. All right, let's do B here. Take row 1 and multiply it by 2. So again, we'll write out space for our matrix. We'll write the operation on the side. So 2 times row 1. So we're taking row 1, multiplying it by 2, putting the result here back into row 1. Our result will be a new row 1. It will replace what we had before. All right, so let's do that here. Row 1 times row 2. Row 1 going back to our original matrix here, so ignoring the result from A. What is our new row 1?
Ignoring A, it means that we need to do it like the previous, like now we need to multiply 1, like 4 will be this one, 4, negative 6, negative 4, negative 8.
Okay, good. So 4, negative 6, negative 4, and negative 8. So normally when we do operations, we kind of do them sequentially and we sort of slowly build a different version of the matrix. Here, we're just considering them independently briefly, so we make sure we understand what's going on with them. All right, so if that's that operation, then the other 2 rows aren't changing, so they would stay the same for 1, negative 3, and 2, 5, 0, 4, negative 1. All right, and then the more common type of operation that we do with matrices, we will take one row and multiply it or divide it by something, and then we will add or subtract that result to another row. So for this one, we are being asked to multiply row 2 by 3 and add the result to row 1. So this will be row 2, and we're going to multiply it by 3, and then we are going to add that to row 1. Where will the result go? We're going to do this operation with 2 different rows. Where are we going to put our answer from this?
Row 1.
Row 1. Okay. So we'll write that here, row 1, and we are adding to that 3 row 2. So it's important to remember or be clear about what our target is. So here we haven't mentioned anything about row 3, so it looks like row 3 is going to stay the same, 5, 0, 4, -1. What about row 2 here? Is it going to be the same from our original matrix, or is it changing?
The same.
It's the same. We're not doing anything to row 2 here. We are using row 2 to change something else, but row 2 itself is not changing. Okay, so our actual operation, row 1 and 3 row 2. So if we can do this in our heads, then that's fine. We could also write it out on the side if we want to be clear with our arithmetic. All right, so let's write this out just to show how we could do this. So row 1, we have 2, -3, -2, -4, and 3 times row 2 here is, so 4 times 3, so 12, 3, -9, and 6. And then we are adding these 2 together. So 2 and 14, that's, sorry, 2 and 12 is 14. Here is 0, here -11, and then here +2. So there's our results, 14, 0, -11, and 2. This down here, this is not necessary. Again, this is just some kind of scratch, some notes here to make sure that we're doing our arithmetic correctly. So if it's a more complex operation, that's useful. It's not necessary. If you can do this operation in your head and be confident you'll get the right answer, then that's fine, and you can do that. Just showing you here how we could represent this. Okay, so the operations that we did here, they're correct. They're also kind of useless because we didn't have any sort of goal. We weren't really trying to solve the matrix, but this does show the 3 different types of operations that we can do. So let's not do this. Let's actually solve a system and get an answer for it. So terms for this, I'll just mention once again, these are called Gaussian elimination, which will be kind of the first half of solving the matrix, and then Gauss-Jordan elimination, which is the second half, so named after some famous math people. Okay, so I have some slides here just to remind us of what the process, or sorry, what we can do and what our process should be. So these are the 3 operations that we just finished doing. Multiply any row by a constant is fine. Adding and subtracting one row to another row is fine. When we do that, we will replace one of the rows in our matrix. The matrix, like, we don't make the matrix bigger each time. We take whatever row was our target, we get rid of it, and we replace it with the result of the operation. And then we can also just swap rows if that comes up, if we see an opportunity. But the multiplying and then adding and subtracting rows, that's the main thing, just like doing actual elimination. All right, let's just talk over the process here quickly, and then we'll go through an actual example. So let's start, or let's say that we start, we have a matrix that's going to look something like this. So we have our right-hand side, our actual values we're trying to solve for, but right now we don't know what they are. And we have just a whole bunch of numbers here for the variable coefficients and the sort of box shape. What's the first goal of solving a matrix, of doing elimination with the matrix? What kind of shape do we want to get? What's our first target?
Triangle.
Triangle. What kind of triangle? Where I can draw lots of different triangles in this. Which parts should be in the triangle?
There should be like diagonal and the half that above this diagonal.
Okay, so diagonal and then above it. So this is call this the upper triangular form, which you'll see in some textbooks. So this, and then the most important part of this are these values here. So this 1, 2, 3. What values will we have in this part of the matrix?
0.
Okay, good. So that's a 0, that's a 0, that's a 0. So we've eliminated, that's the elimination process. All 3 of those should be zeros. Everything below the main diagonal will be eliminated. If it works out really nicely, ideally, we would also have something here in these 3 spots. What values would we have here?
1, 1, 1.
Okay, good. So X, X, X. And ideally, we would have 1s in these positions. It's not crucial, but it does make our job a lot easier. So 1, 1, and 1. If we don't get 1s there, if it's hard to do that, we can do it later at the very end of the elimination process, but it's not necessary to do it at this point with the triangle shape, but you kind of have that in mind. If it does work out to do that, it's good to do it. Okay, so that's the first step. That's the first kind of half of solving it. And then after this, what's our next goal?
All the numbers, each are on the diagonal.
Okay, so we want just numbers on the diagonal, like this. So this is our final shape, just this line on the main diagonal with all 1s there, and then above the main diagonal, these also will be eliminated, canceled out. If we've done that, then either automatically or very easily, we can turn all of these values on the main diagonal into 1s. And once we've done that, then we get our answers here. So the first line, if the y and the x are the y and the z are eliminated, then the first line is telling me 1 times x, so just x, and we have our right-hand side, equals this number. And then this number will be the answer for x. And then the next line will be telling us our answer for y, which will be whatever we solve it for. And the last row will be telling us our value for z. So that's the basic process here. First, we start with the box shape. First goal is to turn it into this upper triangle kind of shape, which I have on this slide here. So this upper triangle shape, the second image here, and ideally 1s on the main diagonal. That's easiest to work with. And then after that, we want to go to this shape on the bottom only the main diagonal. Everything else is zeros. And from there, we have it. So we have our result. So we'll go through the process. Basically, we go left to right. And then once we hit the right, we go back right to left. And we'll go through examples and see exactly what that process is. But that's the goal. So just if you can remember these three shapes that you're trying to make, that should hopefully be enough to help you work through the problems. Okay, we'll do this like a nice, really simple one. This will be a very small matrix here, and then we'll do it. It's almost a little too easy and too simple to bother doing matrices, but then we'll do it for a bigger system where it's a little more helpful. So our matrix here, what is our matrix going to be? You can tell me the whole thing.
2, 1 equals 7.
Okay, so 2, 1, 7. And our second row?
1 minus 2, 6.
And 6. Okay, so there's the matrix. There's our row 1 and our row 2, representing equations 1 and equations 2. What's the first step that we would do with our matrix? Trying to reduce this. Remember, our goal is we want this sort of triangle shape, and we want to have ones on the main diagonal here. Any ideas?
Multiply with minus 2 and minus 1.
Okay, so you want to combine the rows or add the rows or subtract one from the other?
Yeah,
That can work. I see an easier thing that we can do.
okay, R1 minus 1, right?
R1 minus
1.
R1 minus 1, a constant?
Yep.
We can't do that. That is not a valid operation. So we can add and subtract whole rows to other whole rows. We can't just subtract a constant like this. We wouldn't, if we think about the equations we're working with, this wouldn't really make sense. It doesn't stay balanced. I see an easier thing that we can do before any sort of adding or subtracting. I see the easiest possible operation. Okay, so swapping rows. If we have the goal, remember, is to have a 1 in this spot here. So we can do that and then eliminate down to get rid of the other position, the other value in our X column. So the easiest thing we can do right now is just row 1 and exchange with row 2. So we'll just rewrite them as 1, -2, 6, and 2, 1, 7. So now, again, with our triangle form that we're looking for, we have a 1 in the first position of that main diagonal. We also have a 1 in the second position of the main diagonal, but we haven't eliminated here yet. So this 1 is probably going to change. So right now we can't get too excited about that. But Right now, our goal is to eliminate this 2 here. So 1 here is fantastic. Now we want to eliminate that 2. What can we do to do that elimination?
Multiply line 1 and then substitute from this row 2.
Not substitute.
Maybe the wrong word.
Yeah, I think you meant subtract.
Maybe.
Okay,
Sorry.
that's all right. So row 2, and we will subtract 2 copies of row 1. So if we do that, then row 1 is not going to change. We are using it, but we're not changing it. So 1, -2, 6, and we'll write out, I know that the math is very simple here, but again, just for clarity, we'll write out what the operation is that we're doing here, each step of the arithmetic. So our row 2 is 2, 1, 7, and 2 row 1 is going to be 2 and -4 and 12, and we're subtracting. So that will turn into a 0. That's what we want. We want a 0 in this position, but again, it's always good to just verify that you do actually get those zeros to make sure you're doing the right operation. And then the rest here, 1 minus -4, that's a 5, 12, sorry, 7 minus 12, that's a -5. Okay, so we could do this, 5, -5. I don't want to do that because I want to be lazy and I want to combine row operations where possible, so I don't have to do extra rewriting. So what
Divide by 5.
There we go. So we're just going to take the whole thing. I'll write it like this because it'll look a little cleaner. We'll multiply by 1/5 and then just erase those, and 1 and -1. Okay, so this has worked out very nicely. We have a 1 in each position of our main diagonal here. And we've also eliminated each value below the main diagonal. So that's our ideal triangle form here. So now we just have one more small step to do to eliminate the value here in order to, if we just do that one thing, then we've finished off our matrix. I'm going to move all this over a bit. Like this. All right. What is the final operation that we are going to do with this?
Multiply row 2 by a -2 and add it to the row 1.
Okay, so row 1 is our target, so we'll write that here. Row 1. We don't need to say multiply by -2. We can just say row 2 and just say, well, by -2 here. So we'll just multiply by 2, by +2, and then add them together. So we can just write it like this. And that should get rid of this -2 here. So yeah, we don't need to write multiplying by a negative number. That's fine if you want, but by convention, or at least the way I do, you will multiply by a positive number here, constant, and then add or subtract as necessary. So our row 2, we already saw here, this row 2 is done. It is perfect. We've solved for y here. Again, this is telling us 0x and plus y equals -1. It's giving us the value of one of our variables. So we don't want to touch that row. We don't want to do anything there. The only thing that we want to do is finish up row 1. So at this stage, we probably really don't need to write out the kind of arithmetic on the side here, because we have a 0 here and we have a 1 in this kind of top position. So 1 plus 0 isn't going to change it. So that's still just going to be 1. The next position here, -2 plus +2. So that should turn into a 0. That's nice to confirm, but we wanted that to be a 0, so it should be. So no calculation needed here. No real calculation needed here because it should be a 0. So the only position we have to actually maybe do some work to figure out is this, the right-hand side position here. So we'll have 6 and then plus 2 times -1. So that's just 6 minus 4. And that will give us a value of 2 there. So if you're going to write out the arithmetic on the side to make sure you're getting this right, then that's fine. Sorry, 2 times, that is not right. I did the multiplying by 2 too many times here. So 6 minus 2 times -1, that's 4. That's better. Okay, so this final position here is the only one we really need to calculate. So once we go from our triangle shape, and then we are working back up, then usually the arithmetic gets pretty simple. It's just maybe a bit of work to get down to that triangle shape. But this final row here, we have our matrix is done. We have 1s on the main diagonal. We have 0s everywhere else. And then the final line here is just telling us our values. So this is telling us that x is equal to 4. And here that's y is equal to -1. Just double checking with our original system here. 4x, yeah. Okay, so there's our answer for -1. So small system here, but it's good to just sort of see how this works, see how a matrix works with a smaller system, and then we can apply this to a larger system. All right, does anyone have questions about this example? Because the next examples are going to be bigger, so if we have any confusion at this stage, we should clear it up now before we move on.
On second step, when you make 1/5 R2 R1, 2 in R1. I understand R2 minus 2 in R1, but over 5, I didn't understand it. Yep.
Okay, we were just multiplying by a constant here because our result was this. So if we were just combining steps basically because we didn't want to rewrite the whole matrix. If we added that as a separate step, then we would have this. So the result here was 5 and 5. So 5, -5. And then let's say we do one more operation here, 2, 6, to just scale this down. So we don't want 5 and 5, we want 1. We want this position here to be a 1. So we'll just divide the whole thing by 5. So 1 over 5 times row 2. And then that gives us 0, 1, and -1. So that's all we did. We just took these 2 rows and we combined them into one thing.
Yeah, I understand it. Thanks.
Okay. So we'll do that a lot in the later examples as well. If we see that we get something and we just want to flip the signs or scale it down by something, we'll just combine them into one step. So that's a nice thing about the matrices. We can combine and make many things happen at once, but still be able to see what all the parts are with our convenient labels and such. Okay, let's go to our first big system here. So this is 4.84 from our textbook in section 4.5. And we will write this out. So there's nothing special here about this system. It's pretty easy to turn into a matrix. So I will just do that for us to start here. So -3 and 1, 1, -4, -1, 2, -2, 1, and 2, -1, -1, -1. Okay, so there is our matrix. What is the first step that you would recommend?
For R1, to change the -3 to -1 or 1.
Switch the places of row 1 and row 2.
All right, so we can just swap row 1 and row 2 because it's very nice to have a 1 or -1 in this position. And then we can just use that 1 to very easily scale the other things and eliminate downward. So that will take care of the X variable for us. So that's our first goal. Get a 1 in the first position and then eliminate all the things below it. Easiest way to get that 1 is to just swap row 1 and row 2. Sorry, I wrote that in the wrong spots here. Should write that in the results. All right, so I'll write this out. While I'm doing this, you can start thinking about what our next operation would be. Two, -1, -1, -1. Oh. Let's match our colors. Okay. What's the next operation that we would do here? So to remind you, we have a 1 or kind of a 1. It's a -1, but we don't need to really flip the sign. It's not a big deal here. So we have a 1 here. Our goal is to eliminate then this position and this position. So there are 2 different operations that we would want to do to eliminate each of those.
Multiply row 1 by 2 and add it to row 3.
Okay, So we'll take our row 3 and we are going to add 2 times row 1. Okay. So if we do that, our row 1 is not changing, -1, 2, -2, and 1. I say we can do another operation at the same time. So what we have here, this is good, but I want to do one more at the same time because I don't want to keep rewriting the matrix. What else can we do at the same time? What can we do to eliminate the -3 in
We
row
could
2?
also multiply row 1 by 3 and add it to row 2.
Okay, so row 2 and 3 times row 1. Are we adding or are we subtracting?
Subtracting.
Subtracting. Because in row 1 here, we have a -1. So -3 minus 3 times -1, that will give us 3 plus 3, -3 plus 3, that's the 0. So that's how we'll eliminate there. Okay, so that's 2 different operations and we can do both of them at the same time here. We might want to write out some little notes on the side here to figure out what those will be. But we'll write them out. Okay, so you guys can do this as well. I'll write out the arithmetic on the side, but you guys can try to figure it out. Some of you can try to tell me what's the new row 2, and some of you tell me what's the new row 3. So take a moment, try to write out the arithmetic, and then you can type your answers into the chat, or I'll just ask in a few moments. So go ahead. All right, can someone tell me what our new row 2 will be?
Zero, -5, 7, -7.
Okay, 0, 0, -5, 7, and -7. So that's just the result here on the side, and we'll put that in. -5, 7, -7. And our new row 3, what will that be?
0, 3, -5, 1,
0, 3, -5, and 1. Okay, so 0, 3, -5, and 1. All right, since we've done this, we've now, the matrix is done for the x's, basically. We have 1 here, again, -1, but we can flip the sign very easily later. So we have a 1 there, and then we've eliminated everything below. So x's are done. That's the leftmost column, and then we just take 1 step left, sorry, to the right, and we start looking at this position next. We do the y's, but we're not gonna do the top one. Again, it's our main diagonal we're paying attention to. So we're going to look at this position next, and we want to, ideally, we can get a 1 here. What we would do sometimes is say, okay, we can divide row 2 by -5 and turn that into a 1. But if we do that, we're going to end up with some pretty nasty fractions here, and we're going to have to do a lot of operations with those fractions, and that doesn't sound very fun. So for now, we could say, let's skip the turning it into a 1 part. That would be nice, but it doesn't seem to work out nicely here. We can just prioritize eliminating down. That's the main thing to do. Turn everything below that position into a 0. So let's set that as our next goal here. So that, and I'll rewrite our matrix. We'll just continue up over here. Let's just move all this over. All right, so continuing our matrix over here. Row 1, so we know, like, our next step here, we're not going to be doing anything with row 1, so we can rewrite that as is. -1, 2, -2, and 1. And it looks like we're probably not going to be doing anything with row 2 either. We'll maybe turn that into a 1 a bit later, but we want to eliminate the thing in row 3. That's our goal here. So row 2 is going to not change, -5, 7, -7. And now we are focused on row 3 and what we can do there. So what could we do to eliminate that 3 in row 3? So again, we have a 3 in this position, and we don't want it to be there. Basically, we have 2 choices. One of them is a good idea. One of them is a terrible idea. Can anyone see what either of the 2 choices are? No. Okay, I will write out the 2 choices. We could do, I'll write them both here. So our first choice would be, we'll take row 3. Am I going to have enough space? Yes, okay. So we could take row 3, multiply it by 2. So 2 times row 3, and subtract from that 3 times row 1. since we have a 2 here. So we'll have 2 times this 3, so that would be a 6, and then minus 3 times the 2, so 6. So 6 minus 6 would give us 0. That's one choice. Our other choice here would be to do something with row 2. So row 3 and row 2. And we could do 5 times row 3 to give us 15. And then take that and add 3 times row 2. 3 times is -5, -15. So 15 minus 15 would give us a 0 here. So 2 possibilities. One of these is, as I said, a great idea. One of these is a terrible idea. Can anyone tell me which one we should do?
The second one.
Okay, why?
It could give to the easiest way more than the first one.
I'm looking for a little more detail than that. There's a very specific problem that would occur if we tried to do the first one. If we did that, if we used row 1, what would happen in this position right here? If we do row 3 minus row 1, what's going to happen in this position with that I highlighted, the X column?
There will be 3.
Yeah, so we would put a number back in there. Right now it's a 0, and that's great. That's exactly what we wanted. But if we used row 1 here, we would be reintroducing a value for that position. We never want to do that. We've finished the X column, so we don't want to ruin it by putting something else in there. So we're going to, again, we kind of take one step over down our diagonal. We use this one, and that's what we are using to eliminate everything that's below it if we had a really big matrix. But we're not ever going to use this top position because that would reintroduce this variable, which we don't want to do. Okay. So this is the operation that we're going to do. We will do 5 times row 3 and add to that 3 times row 2. So please take a moment and calculate that out if you have some paper nearby, and then tell me what our result will be. Okay, what is our result here?
Zero, 0, 4, 16.
0, 0, 4, and 16. Okay, I think it will actually be -4, -16, but then we could factor that out. So we can see a common factor of -4 here. So we can just reduce this to 1 and 4. So that would be our new row here, 0, 0, 1, 4. And we just need to update our operation that we wrote on the side here to reflect what we actually did. So what do we have to do for this, our little operation note on the side to reflect what we did here?
Multiply by -1/4.
Okay, good. -1/4, because we flipped the sign, multiplying by -1, and we scaled everything down. So we divided by 4, so multiplying by -1/4. Okay, so this worked out very nicely. We now have a 1 in this position, in the last position of our diagonal. So that's great. We don't have a 1 here yet. We can do that. It'll be pretty easy to do that in just a moment. But we've done the eliminating. So that's all those positions there are gone, and that's great. Okay, so we've moved all the way from the left over to the right. We started here, then we did here and went down, then here and went down, and then we got to the last one. So left to right. Now what are we going to do? What's our next? We made the triangle shape. So what's our next target? What's our next goal? What's the next shape that we want?
We want to change
Yeah.
-5 to 1 or -1.
We do. That's not going to be the thing that we do next. We could do that. We're going to get some kind of unpleasant fractions, and there's an easier way of handling it. What's the shape? We went from square shape to this triangle shape. And what's our final shape we're looking for?
Diagonal line.
Okay, so just the main diagonal. So just the main diagonal. And if we draw that here, we see that we need to accomplish that, we will need to eliminate the 7, the -2, and the 2. So those 3 positions need to be eliminated. Which ones are we going to do first? We have 3 things we needed to eliminate. What order will we do these in? What's our strategy?
Find out the second row.
Sorry, can you say that one more time?
Find out the second row.
Second row. So the 7 here?
No.
No. Okay, so the strategy, again, we started with the first position, eliminated everything below. Second position, everything below. We got to the end of our main diagonal. Now what we're going, so we went from left to right. Now again, there's lots of ways we could do this, but the way to do the least work and the most efficient way of doing this, we are now going to work right to left. So just go back slowly the other way. We're going to take our final position, this 1, and we're going to eliminate everything above it. And then we'll move to the next position and eliminate everything above that. We could do the 2 here next, but we would just sort of create, oh, sorry, I will, let me turn off those notifications. We could do this position here next, but we would be creating more work. We'd have to do more arithmetic, and we're creating more possibilities of making a mistake. So the most efficient way, from left all the way to right, and then from right all the way back left for these ones. So the 7 and the -2, those are the next two goals here. So we have this, we want to eliminate these two. So this looks like another case where we can do two different operations at once in one step with our matrix, and get very close to finishing this. So row 3 is done. Row 3 is perfect. We are never going to touch row 3 again because it's exactly the way we want it. Rows 1 and 2, not quite done. So to eliminate the 7 in row 2, what are we going to do? Using row 3, how can we eliminate that? Looking at this column, we have a 1 in row 3, we have a 7 in row 2, and we want that 7 to disappear. Does anyone see the operation we could do? Okay, I'll write this out for us. So what we could do is we'll have our row 2, and we just subtract from it 7 times row 3. 7 times row 3, so 7 minus 1 times 7. 7 minus 7 will give us a 0 here. All right, and for our other one, for row 1, we have a -2 in this top position here. We want to get rid of that -2, and we'll use the 1 that we have in row 3 because that's very convenient. So we'll take our row 1 and we will add 2 times row 3. 2 times row 3 for this position here, and that will turn that also into a 0. So those are the two operations we are going to do. The arithmetic happening here is not too complicated. We probably do not need to kind of write out a whole thing on the side. It's just basically one value to calculate. So we can notice here, this position is definitely going to be 0 because rows, like look at what we have with rows 2 and 3, there's both 0. So 0 and 0, add or subtract or whatever, it's still going to be 0. The next position here, the second column. So row 2, we're not doing anything to row 2, and then we have a 0 here, so that won't make any changes. 7 times 0 is still 0. So that position is not going to change. That's a -5. This next position here, well, that's the one that should cancel out. That's the one that should be eliminated. So that should be a 0. 7 minus 7 times 1, 7 minus 7, that's a 0. Okay, so this final position here is the only real one to calculate. Same thing is going to happen with row 1. The -1 isn't going to change. The 2 isn't going to change. This -2 should turn into a 0. And then we just really have one value to calculate over here. Can someone tell me what these two values will be? For row 2, what's our constant on the right side? And row 1, what is our constant here?
-7 and -35.
Which one's which?
The first one, -7.
For row
And
1?
the second one, yes.
-7.
Negative, and the second one, -35.
Okay. -35. Okay. Looks like we have our values there. Then, so row 2, we can actually finish off row 2 right now in the same step. If we just write a little update here to take out a common factor, and then we can be totally done with row 2. So let's actually do that. What should we, how can we update our row 2 operation here?
Divided by -5.
Right, so divide by -5, multiplying by -1/5. And that will just let us update this to be 1 and 7. Okay, so now we have 2 rows that are completely done. We've solved for our Z, it's 4, and our Y, it's 7. And we're just trying to do our final position here. At this point, just one little last step. And not very complicated. We only really have one thing we could do in our operations. So we have everything else has been turned into 0. So if we're trying to eliminate this position here, the only thing that we can use is row 2. And it's a 2, it's a 1. So just we will take row 1 minus 2, row 2. So that's our final operation here. And this first value is -1. We're probably going to want to flip the sign on that, but let's just do that in a moment. This next value, so it should eliminate and turn into a 0. We can just double check that. 2 minus 2, yeah, that's a 0. Here it's all zeros anyway, so that's definitely a 0. The only number we have to actually do some work to calculate here is going to be this last one. So what is our number on the end here?
It is -7.
-7. I'm looking at my notes, and I think we might have made a mistake here with this -7. I got a different number when I was doing this before. So let's go back and check what our operation was. We had row 1 from the previous step, and then we were adding 2 times row 3. 2 times row 3 was 4. So I think we have a 9 here. Yeah. Okay. So I think we're going to have to update that other calculation as well. +9. Okay. Sorry. So let's try this one again here. Now what are we going to have?
It's an 11.
You said 11?
Yep.
So, okay, let's write this one out too. Our row 1 is 9. And then we are subtracting 2 times our row 2 value, which is 7. So what is this?
-5.
That's -5. So -5 here. And let's, again, we don't want to rewrite the whole matrix. So let's just do a little update. We'll multiply all of this by -1. And we just, not that part, erase our negative signs. And there's our matrix completed. So our whole solution here then are X, Y, Z coordinates are 5, 7, 4. So we get the X equals 5 from the first row, the Y equals 7 from the second row, Y equals, Z equals 4 from the final row. So there is our solution. Okay, this took a little while, I know, because we're talking through the process as we do it, but being able to combine our steps, do them all at once, or do multiple steps at once, it saves us a lot of kind of extra writing. And we just kind of, I have to write it in like 2 parts because my screen is very wide and not very long. But normally when you're writing this on paper, it just becomes one just sort of nice organized column, which you can kind of see in my, I don't know how well this plays on camera, but just my notes, it's just nice vertical column showing the whole process. Okay, let's hop. I'm going to erase this if you want to take a screenshot or something right now. All right, so I do, question?
No, it's fine.
All right, I do have 2 more examples. Based on our time, I don't think we'll have time to go through both of them. The next one's going to be a bit shorter though, so we can get through one at least. Let me just go back to this and just sort of repeat what our process was. So the next example is actually going to work a little differently, but typically, again, we start with the box and we just work down our main diagonal. First position, choose one variable we're going to solve for, and then eliminate everything below that. Then you'll get to a system with 2 equations and 2 unknowns like this. And we're taking the next position, eliminating everything down. And then we get to a system with 1 equation, 1 unknown. That's pretty easy to solve for. And then we do the same thing and we go back up and going from right to left now. So eliminate everything up, that, and then again, 1 step left again, up, eliminate that until we hit the far left side, and then we are done. You don't need to do it in this order. There's lots of ways you could start with Y first or Z first or whatever. You might get yourself a bit confused if you do it that way. Our next example will be different like that. But if you kind of follow this pattern, this is how you do the least amount of work. It's the most efficient, rather than reintroducing a variable somewhere where you've eliminated it or doing extra arithmetic steps. This is the least amount of work following this pattern. All right, this one was the one I wanted to look at next. So we have this system here. I'll ask you to tell me what the matrix will be, because this one, oh, it's a little different from what we have normally. I have to go turn off an alarm. 1 second. Okay. So let's try this one. Can someone tell me what our matrix will be? What's the first line of our matrix for this system?
3, 0, -1, -3.
Okay, good. So 3, 0, -1, -3. So we have to notice the y is missing here, and then that has to be written as a 0. All right, so the rest, if we just notice that, then 0, 5, 2, -6, and 4, 3, 0, and -8. So there is our matrix for the system. We have a few different ways we could do this. If we took our first position here and tried to turn this into a 1, then we'd end up with some unpleasant fractions here, or 1 here. A 3 and a 4, those don't really cancel each other out really nicely. So we could do that. We could say 4 times row 3 and 3 times row 4. Excuse me. But we could also do this a different way. Just for some variety, I want to show you what that would look like. So let's say instead of starting with the X, we'll start with the Z position here. So let's treat Z like our first column, and then we'll eliminate the Zs and then kind of work from that. So kind of doing this a little backwards from what I was just telling you, but it is the same process. It just looks like it's a different order. So let's say we want to start with this, and we're going to eliminate everything else we find in this column. So we have a 0 at the bottom, which is great. We don't have to do any work there, but we do need to eliminate the 2. So we'll make that our first goal here. So if I want to eliminate the 2 in row 2, the Z coefficient in row 2, what operation will we do?
Row 2 plus 2 row 1.
Okay, so take row 2 plus 2 times row 1, and then that will eliminate that. Okay, this one is not a particularly tricky operation here. So if we don't need to write it out again, then there's no need. So we have a 0 here, right? Like in our original. So just 2 times 3 plus 0. So that's just going to be 6. Here we have 0 plus 5. So that's just 5. Here, this is canceling out, or supposed to, and yes, we can confirm it does. So that's a 0. So the only position where we're doing any real math here is this last one. And what will we get there?
-12.
-12. So -6, and then plus 2 times -3, so -12. There's that position. Okay, so we've already eliminated this down to be a 2 by 2 system. The Zs are fully eliminated from that column. So kind of, we have to sort of skip over this part, like in our brains, and just sort of imagine that we have this or see the 2x2 system that we have here, but it's still, we've reduced the complexity, so it still works. It doesn't look quite as nice as our previous ones, but we're still accomplished. We're still making progress here. Okay, so our next goal then, we have this position, and we're going to eliminate everything below that. We could do the x's or we could do the x as well. But actually this looks pretty nice because we've already have something eliminated above. So the y's look like they're a little easier to work with. So we want to eliminate this 3 here. So trying to tell me what operation we can do to eliminate the 3 in row 3.
Oh, 5 row 3 minus 3 row 2.
Okay, so we'll take 5 times row 3, which would give us a 15 there, and then subtract 3 times row 2, 3 times the 5 will give us a 15 there. Okay, that looks like it'll work. So this should give us a 0 here. And this other position, those are both zeros. So that will be a 0. That's very easy. So we really just kind of have 2 numbers to calculate, here and here. So you guys can take a moment and try to tell me what those 2 values will be. All right. Do we have our values for these 2 positions? Say 2, and we have 2 positions. So what's our other one?
2 and -4.
Say 2 and -4, like this. Okay. We see a pretty easy simplification that we can do. Common factor of 2 we can take out. So let's just do that at the same time. So multiply the whole thing by 1/2, or just divide by 2. And we'll rewrite this as 1 and -2. Okay, so we've solved for x now. The previous one we solved for y first. Sorry, we solved for x first. No, sorry, we started with the x's. We solved for z first. That was the one that when we went all the way to the right. But here we've gone in the opposite direction, and we started with z, we worked left, and we solved for the x first. But we still have that triangle shape here. We have 1 row where 2 other things have been eliminated, and then we have 1 row where 1 other thing has been eliminated. So we've also, just by chance, we've eliminated this upper position here. So we've made a lot of progress, and this is still working. It might look a little different from the sort of standard way of doing this, which we had in the previous example, but it is still working. All right, let's continue this up over here. And the next thing that we will do with our matrix, we have a few more operations. So I see two next things that we can do. What is our target? What things do we want to eliminate next?
Six and 3.
All right, the 6 and the 3, those are the only things left at all. So we're going to use the one that we have here, and we're going to eliminate the two things above it in that same column. All right, and to do that, what are we going to do? What operations will we need to do?
Row 2 minus 6 times row 3.
Okay, so row 2 minus 6 row 3 would be one of them. And our other operation?
Row 1 minus 3 times row 3.
Minus 3 row 3. Okay, so both of those will work, and there's not going to be a whole lot of actual math that we'll have to do here. So this first position for row 2, that should be a 0. It's supposed to cancel out. So again, we can just do a quick check. So 6 minus 6, yes, that's 0. Okay, great. We have a 0 here, so that value is not going to change. We had 2 zeros, so those are just zeros there. And then the other one that we will be calculating is this last position here. So what is our number there? We also have the same thing happening in row 1. That's a 0 there. That's a 0. That's not going to change.
0.
0 here. Okay, that's an interesting result. We're going to talk about that in a moment. We also have a value here for the last position in row 3. What is that value going to be?
Three.
We say 3. Okay. All right. So our row 1, we have a -1 here. So that's just, let's just flip the sign on that right now. That's not very hard to do. Let's multiply the whole thing by -1. And that gives us a positive. And that gives us a negative there. Okay. So there's our x value solved. Our x is equal to -3. Here's our z value solved. Z is equal to -2. Sorry, I'm used to thinking that the first row is giving us our first result. It is not. Sorry, this first row is actually giving us our z value because this is the z column. So 0 times x, 0 times y, 1 times z is -3. So let's try that again. So our z value is -3. Our x value, because this is the x column, is -2. what is our y value here?
Y equal to 0.
Okay, so y is equal to 0. So we could take this, and with our row 2, we could divide everything by 5, but it's really not necessary because we have a 0 on the far right, so it doesn't really matter here. Note though, it is not the same as saying this. So we can't reduce down and say, well, it's just 0, 0, 0, 0. Why are those two things not the same? That's something that we could possibly kind of get confused about here. If we had that kind of result where we had a matrix, if we had a matrix where one of the rows was 0, 0, 0, 0, what would that mean in terms of the solution? Right.
0 doesn't assign to any row or any column, which means 0 is not equal to y or z or x.
So this would mean like 0x and plus 0y plus 0z is 0. So 0y equals 0. 0 equals 0. When we're trying to understand the solution or how many solutions there are, how do we interpret a result like this? We haven't really talked about this with the 3x3 systems, but we did talk about this when we looked at the 2x2 systems, and we looked at the possible algebra results and then what that means in terms of the actual lines that are happening. So if we get a result like this, where we get
No limited solutions.
right, so there's an unlimited number of solutions. There would actually be some restrictions based on whatever the x is equal to and whatever the z is equal to, but there is an unlimited number. So basically the two, we'd have planes that are intersecting and there's sort of a long line of solutions. So it's an infinite number of solutions if we got a system like this. But here we don't have this. So the line here is telling us 5y is equal to 0. The only way for 5 times something to be 0 is if y is equal to 0. So y is a very specific number, and that number is 0. It's not this infinite solution. So those two cases might seem kind of similar sometimes. It's important to recognize how they are different. So here, our solution is -2, 0, 3. If we want to, we could rewrite our matrix in kind of the more standard looking way. 1, 0, 0, -2, 0, 5, 0, 1, 0, 0, and 0, 0, 1, -3, like this. So this is the more standard way of looking at it. And here is our nice main diagonal line here, showing the final, the totally solved version of this matrix. For our purposes, we don't, if we solved it in the other order, it's fine if it kind of looks like this. It's just everything is eliminated. Everything else outside there is zeros. That's the main thing. But there are places and things that we would do in math where we would want to actually have things specifically in this order. You kind of line them up with the main diagonal Again, we personally won't, or in our class, we won't get to those things, but there are other things in math so that involve that. So it's nice to just stick with the convention and the style that most people use. It does come in handy in other places. Okay, so this was a system I wanted to show you how we could approach this if we did have a bunch of zeros in our original system over here, and how we could handle that. So we had to kind of introduce an X value over here with this 6 so that we could create a 2x2 system and then solve from there. Also, where we can start with a different variable. If it looks more convenient to start with the Z values, that's possible. We can do that. You just kind of want to avoid doing unnecessary extra work, but this one worked out very cleanly to just start at one side, go all the way over, then go all the way back. We could also start with the Y's first if we felt that was more convenient. So lots of choices. They'll all work out in the end. Hopefully, kind of the most standard, start with the X's, then the Y's, then the Z's will work out, but that won't be every time. So it's good to have some flexibility. Okay, I had another question, which was this one. The solution here is actually, it's not too hard to work with. We just do one little step at the beginning to maybe get rid of these fractions if we don't want to deal with them. But then the rest of this isn't terribly surprising. So we won't do that for sake of time. But that looks like what we wanted to cover. I'll just throw this back up again. Does anyone have questions they would like to ask about this matrix process, this elimination process? Okay. Are you confident that you can do this? Does it make sense? Do you think you could work through one of these problems on your own?
Yep.
Yeah, no problem?
I think no problem.
Okay. So there's the homework question. One of the homework questions is solving a 3x3 system, specifically using a matrix. So that'll be a good test of it. Hopefully it's not too tricky. Again, if it does feel weird or it feels confusing, just remember, imagine whatever you would do if it was a system of equations, then do exactly that same thing, system of equations and doing elimination, then do exactly that same thing with a matrix, because it is the same thing. We're just writing the numbers in a box instead of as lines, but it's the same process. It's all the same concepts. Okay, I think we're done. I'll just wrap up. We didn't get to the last question. That's okay. Hopefully the homework isn't too tricky for you guys, and then we'll have another weekend. Just one day of class really for us, and then another weekend, and then we'll meet again next week. Thanks for coming. Enjoy the rest of your evening. See you next week.
Thank you so much.
Goodbye.
Bye.
Thank you, Professor. Goodbye.